Okay, so welcome everybody. Sorry for the very slight delay. It's the first of the Menten Institute talks here in Manitoba. So we had a few settings to run through. Welcome to the Menten Institute online or in-person presentations. It's my great pleasure today to be hosting Amy Hurford. Very briefly, Amy got her master's from the University of Alberta. She then went on to do a PhD at Queen's, did a brief stint as a postdoc at Fields, and then started at Memorial University of Newfoundland. Apparently you have to come here. So she started in Newfoundland in 2012, I believe. And so, yeah, it's a great pleasure to have you here, and I'll let you get on with it.
Perfect. Thanks, Julianne, for the introduction. Oh, thanks, Graham. I'm not going to do this because should I just go over here in the corner? Is that good?
What in case you maybe push a little bit the table and.
I'm good. Thanks very much. Yeah, so my talk today. Is that okay online if I go like this?
Yeah, yeah.
Okay. So my title, I said, pandemic preparedness is modeling preparedness. And the goal of the talk was to reflect on the COVID-19 pandemic and try to understand what it taught us about modeling preparedness. There's three parts. So first, I'm going to talk about some technical issues. Then I'm going to talk about the modeling philosophy, and I have a few slides at the end about the profession. Okay, so the first part is to talk about some of the technical issues associated with the models that we use for the pandemic response. One of the first pitfalls I'm going to talk about applies to models that have continuous dependent variables. But before I talk about the flaws in those models, I just wanted to quickly say that I really like these models and they're really helpful. So before we talk about their problems, I want to just also make sure we mention their strengths. So many of the models that I did during the pandemic were deterministic models, ordinary differential equation, compartment models. This is an example of what I'm talking about. So at the top there, you see the different compartments. They're different infection states, susceptible or latently infected. This is formalized as a system of ordinary differential equations. And then I have a picture of the type of output. It's a continuous variable on the y-axis, the number of clinical infections. So these are like real numbers. And this is an example of the kind of thing that you can get out of that. This is something that I call Don't Wait, Re-Escalate. It has a catchy title. And this figure is showing that if you wait longer to implement restrictions, that's really just going to make them need to stay in place for longer. So you don't wait, you re-escalate and implement the measures. But that's kind of what's useful about simple models. Like, I know this is not the most exciting mathematical thing, but simple models are valuable as stylized facts for communication to non-modelers, and flatten the curve was a very famous example of this. I don't know that the original graph was made with an SIR model, but it easily could have been. And you can make that point with a really simple model, and this type of thing was really impactful. I think this was also an example of this. Simple models as stylized facts being very impactful was also the case when the Omicron variant came. It was known to be less severe but more transmissible, and was going to place an extreme burden on the healthcare system, despite being less severe. So both of those points, I think, were quite important, but you don't really need a super complicated model to be able to make those arguments. And it's probably better to not make a complicated model if the goal is to communicate with non-modelers and the public. Another really strong point in the favor of simple models, in this case, like models that solve really fast, is that the parameters are often unknown, and doing sensitivity analysis is possible for models that run really quickly. Usually these are ODEs or compartmental models, but I guess I am conflating some different types here. But like this really is an issue, right? And this is an example from the book Ecological Forecasting. And it just really makes the point, I think, about how like how much runtime can actually matter. So in this instance, you imagine a model, you have 20 parameters, which is pretty common, I imagine, in the field. You want to consider 10 different values of each parameter because maybe you're not really certain of the values, and it takes 1 second to run your model. That setup of the problem doesn't sound that unusual to me for a lot of things that I would do, but the thing that is stunning is how long it would take to run that model. So the answer is it would take 10 to the 20 runs. They're each taking 1 second. And if you started your simulation immediately after the Big Bang, you'd only be 0.4% complete now. I mean, you can't actually do this probably with flattened hypercube sampling, but the point is that there are really compelling reasons for why you want models that run fast, and sensitivity analysis is one of them. So having talked about the strength of ordinary differential equations and models that have continuous dependent variables, such as infection prevalence, let's start talking about why they were some of the problems that they have in terms of trying to model COVID-19 in Newfoundland and Labrador. So this is what I call I guess I don't call it, Dennis Mollison calls it the atto-fox. And the atto-fox is sort of an examination of this paper by J.D. Murray and colleagues, and it's about rabies in England. And this is a traveling wave, so you kind of need to look here, and it's going 100 kilometers per year this way. And this axis here is space, but you can, I guess, imagine it, that space axis moving at 10 kilometers per year. Over here, the foxes are carrying capacity and there's no infection, but you get to this point in space where some foxes are infected. You've got rabid foxes and incubating foxes. Lots of them are dying because you see the susceptible foxes mostly getting killed here. And then across space, they're kind of recovering a bit. And then there's the second wave back there. So this is kind of like a main conclusion of the paper, that you can have this resurgence of rabies 6 years later in England. Yeah, and the other thing that I would say is, yeah, ultimately, the next slide is going to talk about how these results are like mostly an artifact and a technical error. But this is actually quite a good paper. Like, I don't really mean to slam the entire paper. It's like actually very nice in terms of the math biology that goes on there. So I just wanted to note that too. So what causes the atto-fox problem? So if you're wondering what the atto-fox is, it's 10 to the minus 18 of a fox. Atto is the abbreviation for 10 to the minus 18. And continuous dependent variables cause the atto-fox problem. So I guess I like the way it's phrased in the paper. As to the second wave, close inspection shows that the explanation lies not so much in the determinism of the model as in its modeling of the population as continuous rather than discrete, and its inability to let the population variables reach zero. So the density of infected foxes declines to a minimum of around 1 atto-fox, 10 to the minus 18 foxes per square kilometer. Then the model allows this atto-fox to start the second wave as soon as the susceptible population has sufficiently regrown. So that is the atto-fox problem. It's to do with continuous, in this case, number of infected foxes. And because that's a continuous variable, it doesn't ever go to zero. It just gets very close to zero, but that's a bit problematic as it allows for disease to resurge. And that's, I mean, practically speaking, this 10 to the minus 18th of a fox is not going to cause a second wave, but if you don't stamp out those very small foxes, they are going to cause terrible artifacts in your models. So this is about not so much that it's a deterministic formulation, because I think a lot of us might think, well, we'll solve this problem by going into a stochastic framework. It's the fact that the variable is continuous rather than discrete, and it just gets close to zero. It doesn't actually equal zero. So to summarize, the first pitfall of like a technical point and a technical thing that I learned about modeling during the pandemic was to do with the atto-fox. This problem concerns models where population variables never reach zero, and this enables a rebound from very small values. It affects modeling where public health measures are released, because you can't really release the public health measures because you get this artificial second wave infection. Any problems where you're looking at elimination strategies or travel measures, because you just can't eliminate unless you do something about these arbitrarily small number of infected individuals. And problems that are looking at the transmission dynamics where you have clusters of cases rather than community outbreaks. What are some solutions to this problem? You can just end the outbreak when a small value of infection prevalence is reached, say like 1 infected fox per kilometer, just end the simulation then. So mathematical analysis in that framework is in Hansen and Day. You can model the outbreak duration and the time between outbreaks. So you just model the outbreaks and then you come up with some model that tells you how long it's going to be between the outbreaks. And the importation community spread switch model is a last solution to this problem. So the bottom two are like approaches that my group has come up with, and I can talk a bit more about them. The second big technical problem that you can have if you're trying to do modeling for Newfoundland and Labrador, which is a place I guess I showed in the beginning, the COVID-19 reported cases for Newfoundland and Labrador, but during the pandemic, for long periods of time, Newfoundland and Labrador would only report travel-related cases and no community spread. So it's an example of a region that had clustered cases, some rare community outbreaks. It's also an island, and the second pitfall is sort of a hypothetical scenario that in this paper by Joel is called the island of Transmithica. So again, I really like how the authors frame this. So let me quickly skip forward to, I wish I could read this while also showing the figure, but I don't have those skills. This is the figure, and hopefully you can see the gray shaded regions and the black, which is the averaging of all of these curves that are representing epidemics that are starting on different hypothetical days. So these are all some scenarios, epidemics that are all starting on, there's one starting on all these different days. This is some modeling that some modelers have done, and they want to summarize all those curves into some summary statistics. The summary statistics that they come up with is this median, and there's some kind of descriptive interval from 25 to 75%. But what you should take from this figure is how poorly those statistics summarize the actual individual curves. All right, so remember the picture in your head, and that will tell the story of the island of Transmithica. So 1 million people live in complete isolation from the rest of the world. A virus has ravaged the outside world, and in the process, all viral parameters have become known with perfect precision. As Transmithica slowly opened up to outside visitors, the inhabitants knew everything about the virus, except when it would arrive. The leaders of Transmithica asked their epidemiologists to estimate how the disease would impact society. The epidemiologist simulated a number of scenarios, all with perfect choices of parameters, but starting the epidemic on different dates. Their simulations produced an ensemble of epidemic curves, and thinking that the individual simulated epidemic trajectories might clutter the picture, they presented the fixed time summary statistics shown in gray and black. Thus, the islanders prepared for an outbreak that might infect between 2,000 and 3,000 individuals at its peak. As we can inspect, however, from the ensemble of the time displaced curves, the actual peak impact in every single case is more than 4,000 cases. So you'll see that in the next slide, which we try to keep in our mind. Each of the individual curves has a much different peak than if you try to summarize the curves together by taking the average. I mean, it does a horrible, horrible job just trying to take that time average. Okay, so I mean, this is really the problem. This is really exactly the situation that we had with trying to model COVID-19 in Newfoundland and Labrador much of the time, is that we didn't know when a community outbreak was going to start. So I think you really have to be careful when you're doing modeling in that situation, because you could easily make mistakes by averaging across outbreaks that are hypothetically starting on different dates. So to summarize for this second pitfall, it's called the island of Transmithica. It concerns uncertain start dates for community outbreaks. This affects all models. Like, you're not going to get around this by doing agent-based models or stochastic models. It's about trying to summarize runs of multiple simulations with different start dates. It affects regions that have no community outbreaks when you're trying to figure out what would happen if there was one. It's going to affect models that are linking importations to community spread. So there's a lot of times these models that will link those two. It also affects ensemble forecasts of hospitalizations during COVID-19 pandemic in the Netherlands. That's what the paper is about. Like, it starts with that island of Transmithica example, but then the reason they did that example was to explain problems that they were having in their own analysis in that application. So it certainly comes up in more applied contexts. And I think the example, the story that they tell, is just to really drive home how easy it is to make that mistake and not even realize you're making it. The paper also has, I think, probably the best recommendations on how to not make that error. So one thing is to do curve-based summary statistics, like the peak. If you're interested in the peak, like, just report that the peak was 400 cases in every single time instead of taking the average at a fixed point in time. And then summarizing estimated likelihoods of specific scenarios of interest, so the probability of the outbreak starting on each of the days. And then third pitfall, like things I learned from the technical side of modeling COVID-19 to watch out for, is overgeneralization from regions that are experiencing community spread. So not all regions are going to be having community spread. And I wanted to go back to the way that the World Health Organization was classifying different types of cases reported of COVID-19 in different countries. So you see that, this is just part of the report today. So you can either have community transmission or clusters of cases or sporadic cases. And community transmission, that's a large outbreak. Clusters of cases is experiencing cases clustered in time. And then sporadic cases are kind of the same as clustered cases, but it's they're imported or locally detected. So the point of this is to say that not every region is experiencing community spread. The opposite of community spread would be these clusters of cases, which I think reflects the Newfoundland and Labrador situation in many times. There's some other literatures that seem to be having like similar sort of ideas about, I guess I'm trying to come up with a framework that could handle both community spread and clusters of cases. So there's a few papers that try to look at parallels between biological invasions of like invasive species and also emerging infectious diseases. In this literature, you will see more these chronological stages of risk. So they're looking at introduction, establishment, and then invasion. So the biological invasions literature sort of makes these like slower steps from translocation, and then these sort of like establishment, like these smaller outbreaks. So that could be like one sort of modeling framework to try to draw on to like better understand clusters of cases. But this problem, I think, also comes up in zoonotic spillover. So in this paper, there's these different stages that different infectious diseases might be, and there's zoonotic infection spilling over into humans. The stage 5 one would be an infection that's only spreading in humans. The stage 1 is an infection that's only spreading in animals, but you've got some interesting stages in between that. So stage 3 is called stuttering transmission. This is like clusters of cases. It's like the reproduction number in the, say, humans is less than 1. And so you just get these clusters of cases. And stage 4, the R0 is bigger than 1. So you get the sustained transmission. That's where the community spread model would be applicable. So these all the literatures are kind of handling some of the ideas. This is another picture, I guess, of the stuttering transmission. So you've got these infection chains that are going to going to extinction. And if instead of thinking about the zoonotic spillover problem as there's an animal reservoir with infection that's spilling over into humans, maybe you could just imagine that there's a reservoir of infection that's mainland Canada. And like, what's the chance of the infection in that reservoir, which is mainland Canada, spilling over into Newfoundland and Labrador, and try to approach the modeling from that point of view? That seems like, you know, basically what we're seeing with Newfoundland and Labrador is we've got this stuttering, what would be called stuttering transmission in the zoonotic spillover literature. So to summarize from pitfall number 3, overgeneralization for regions with community spread, this concerns using community spread models like SIR, which is like kind of the first model that you think of when you want to model epidemics, and recommendations from regions that are experiencing community spread. You take those models and you take those recommendations, and they just get applied to regions that have clusters of cases or stuttering transmission, without stopping to think that they actually don't apply in those regions, and not every region is experiencing community spread. It affects regions without community spread, and also underserved and under-resourced jurisdictions that don't do their own modeling, but they're just looking to other jurisdictions for recommendations and models and just taking them without realizing that they're actually not applicable, because those are community spread models and the community spread isn't in place in the focal jurisdiction. All right, so what are the solutions to the third pitfall? So the first one is maybe not very nice. I put just do the modeling correctly, but in some respects, like just don't use community spread models for problems that are not community spread. So just obviously don't do that. Multi-jurisdictional representation would help to have other voices in the conversation to say like, oh, I don't know if that's exactly what's happening in our jurisdiction. Maybe we need a larger suite of models here, a larger suite of recommendations. We could also serve and resource all the jurisdictions so they could have their own models and come up with the right ones for their jurisdictions. Another solution is the Canadian Small Jurisdictions Working Group. We try to draw attention to these issues. Okay, so what are some solutions? This is Maria Martignoni. She did her PhD at UBC Okanagan and then was a postdoctoral fellow. And she came up with a solution to, this kind of solves the atto-fox problem, I think. So her approach was to model the outbreak duration and the time between the outbreaks. And yeah, this is a picture of what it looks like. Like I said, it's getting around the atto-fox problem. And so what Maria does is we have like a little model. So the red people are community infected people. They get that community outbreak gets started by the blue person, someone who has some history of travel. And then there's a bit of a community outbreak, but it ends up going extinct. And then we sort of like artificially end that. We decide that problem is over. And then we like consider a variable that describes when is the time until the next community outbreak. And then we like look at the characteristics of that one. How long does it last. And one of the things we were interested in here is what proportion of the time do you have restrictions versus not have restrictions. So after you've extinguished all the cases, then you can have mild restrictions. So you see that in the green. And this was Maria's approach. It's a little bit more about it, and it's published. So we're interested in the percentage of days with mild restrictions, and so long as the time between the outbreaks is sufficiently long, then you can have a period with mild restrictions. And like I said, like this is overcoming the atto-fox problem by just deciding that the outbreak is over if there's a low number of, if there's low infection prevalence. And so, yeah, that was Maria's approach. And like we came up with the actual, I mean, it doesn't need to be a stochastic model. I think I said that earlier. So this was just like a very simple, it was really just two linear population growth stitched together. So we had analytic expressions for how long it would take to get the outbreak down to the level where we would say that it was over. So Maria had an analytic expression for the duration of the outbreak. We treated the time between outbreaks as a variable, and were able to figure out the percentage of days when you can have mild restrictions that way. So it's a really simple model, but it gets through that problem of the atto-fox. I also feel like it wasn't that easy to know how we were supposed to fit this time series of cases in Newfoundland and Labrador. Like I said, you kind of can't really just fit SIR to it because for a lot of times there isn't any community spread. So this is how I think you do that, how you would fit this time series. So I call it the importation community spread switch model. That's essentially all it is, just piecing together a model for importations and a model for community spread, and just switching between those two depending on if your cases are being reported through the mechanism of importation, or your cases have been driven by importation, or if your cases are being driven by community spread. Maybe this figure isn't super easy to see, but the dark red are travel-related cases. So these are people that during the pandemic came to Newfoundland and Labrador. They were reported as a COVID-19 case, but they were also required to self-isolate for 14 days. Anyone who came to Newfoundland and Labrador in the time period was required to self-isolate, infected or not. So having travel-related cases be reported wasn't super consequential because there's really only the entire time until February 2021, there's actually no infection of these infected travelers, caused no community outbreaks. In February 2021, we had the Mount Pearl outbreak, so like one instance of a spillover event from the travelers. And then there was this small outbreak later of the Delta variant in Central Health. But across this entire time series, there's only like 2 or 3 occurrences of community outbreaks, travelers infecting community members. And the blue is the model fit, and that was done by Zahara Mohammadi and Steve Walker using Menten too. Just to say a bit more about this approach. So the data are the incidence of travel-related cases. That was the dark shading, and the light shading is community cases. Most of that time series is just dark. It's just travel-related cases. To do that fitting, we include a model variable that's travelers in isolation. So those travel-related cases, like we just come up with some rules and assumptions about like whether that person is currently infectious and could cause a community outbreak. We do the fitting by saying 10 days before a reported community outbreak, we're going to briefly allow the rate that an isolating traveler infects a susceptible community member becomes positive. So we don't want the start of the outbreak to be uncertain. We want to fix it. And we're going to say that it happens 10 days before the reported outbreak, just due to lags with reporting and testing, etc. At all other times, there's no connection between the travel-related case layer and community infection. So we just open the gate to start a community infection. We turn the switch on at a time that makes sense given when the community cases are in that data set. And also, if infection incidence gets small because we're starting to get rid of the outbreak, then you set it equal to 0. Otherwise, you're going to cause an artificial resurgence. So features of the importation community spread switch model is that it overcomes the atto-fox problem by artificially setting small numbers to 0. And it overcomes the island of Transmithica problem by fixing the start of the community outbreak just based on what is obviously part of the data. And the start rate is not treated as uncertain. But I also want another really strong contribution of mechanistic models during the pandemic was scenario modeling and counterfactual simulation modeling. So I don't know that we really have that framework in place yet. So far, we've managed to fit one of these clusters of cases time series, but I also want to come up with a counterfactual, a framework for doing counterfactual simulations. So these are some examples that I have down the bottom there. The dark band, that's like your travel related cases that are people that are in isolation. And then you can see in that picture that sometimes I have some community outbreaks happening. There's 4 that happened in simulation 99 and a little one that's starting towards the end there. Okay, so this is how we want to do our scenario modeling. You can start the outbreaks on different dates, right? They start on different dates, the community outbreaks on simulation 22 and simulation 99. But you just want to think about how you're going to report those summary statistics, right? So you could look at the number of community outbreaks that happen. So it's kind of like there's 5 that start in simulation 99. So you could say how many community outbreaks happen on average across my simulations. You could say what's the average size when a community outbreak happens. You could say the average days without any community cases, but you are not going to average the prevalence at a given point in time across simulations, and you are not going to attach any meaning to the date that the outbreak starts. Like it's not really that meaningful that the outbreak starts around day 200 in simulation 22. That's just a stochastic thing that could happen. Okay, so the other thing that I sort of realized when I was doing this is it's a bit undesirable to have, like, I don't think you want to treat the start date for the community infections as a random variable that doesn't consider some of the really sensible data that you have available. So if you're doing these counterfactual scenarios for regions like Newfoundland and Labrador, how do you figure out when a community outbreak might start? And from that, I think you want to consider the travel-related case data, because it would be really, I think you would look really silly if you tried to do a counterfactual scenario where you said an outbreak, community outbreak started on this date when there were no travel-related cases at all. Like the travel-related cases, those people failing to self-isolate and getting into the community, that is the mechanism to start a community outbreak. So you should take into account this data on travel-related cases when you start to do your counterfactual simulations and you have these community outbreaks starting on different days. So this is how you might do it. So you start with the travel-related case data, that's in the top and that's in the black. And then you come up with some kind of model to go from travel-related cases to travelers that are infectious and in isolation. So that sort of like spreads out the black line a bit more into the green curve because they're going to be infectious across some period, right? So now you have the green curve and you can see that the green curve is like highest. That's when you have more travelers that are self-isolating and infectious, when you have more travel-related cases, but you know, the thing kind of gets, it's spread out across time in the top there. So what I do is I take that green curve and I turn it into an empirical cumulative density. And then to figure out when my community outbreak starts, say if I want to have one community outbreak, and okay, so you take a random variable, and I guess I got 0.64. I take a random variable between 0 and 1, 0.64, and then I map it across to my empirical density, and then I find out that the outbreak, that it's going to start on the 27th of April 2021. So this is a way to use the data on the number of travel-related cases to figure out what's a sensible day to start your spillover risk, or sorry, to start your community outbreak. And you could be even more fancy about that. Like that was just sort of like an illustrative example of going from travel-related cases to the chance of infection happening in a community member, which I call spillover into the community. But like even more fancy would be to take like all these data sources that I tried to aggregate together in this paper that's cited down the bottom, because whether spillover happens, that's going to depend on, well, we already saw importations as a data stream there, so that's fine. But the spillover, that's going to depend on how much vaccination there is in the community. And it's also going to depend on the self-isolation or like the non-pharmaceutical interventions that are in place in the community. Like if there's capacity limits when the traveler spills over into the community, that's going to be less likely to cause an outbreak if you had like these really strong gathering limits in place at the time. So taking all of this and making the bottom plot, which was the aggregation of those data sources, you could make that into a cumulative density, use the same approach, and now you've come up with a more realistic spillover model that includes things like pharmaceutical and non-pharmaceutical interventions in the community of interest. So to summarize what we learned about the modeling from our pandemic experience, we could model outbreak duration and the time between outbreaks. We have an approach to fit and simulate using the ideas of the importation community spread switch model. And I think those are good ideas, but I haven't really been able to publish them yet. And another thing that I think we learned about the modeling, I'll say a bit more about this later, is that we need more modeling frameworks that are general so that they can handle both community outbreaks and clusters of cases. But also, I think we need more general modeling frameworks where a range of public health responses are potentially optimal. I'll say more about that later, but you probably heard about like elimination strategy or mitigation strategy or circuit breaker strategy. We need more models that could recommend any of those from one general framework, because often those health responses are just treated within one paper without coming up with a more general framework. All right, so now I'll talk about the philosophy. So that part was very technical. Now we're thinking more philosophical, and maybe this is less interesting because I feel like these have always been questions that have been around in modeling. What type of models to use, mechanistic or statistical? Should we use agent-based models or compartmental models? And should we be doing region-specific models? I guess Caroline Colline also, I think, calls this, like, do we provide modeling as a space station, or do we have modeling fire stations? So fire stations serving the local community, space stations serving the global community. I'm wondering when I should stop talking. It's like, do I go all the way to the hour? Do I stop for 10 minutes?
I think we have 10 minutes of question at the end, but
Yeah. Okay. Yeah.
So we have 10 minutes.
Yeah. So I'd stop in 10 minutes?
15. Yeah, we are.
Oh, sorry. This is the framework that I'm going to handle this question of travel, of mechanistic versus statistical models. This is something that I had running on my computer for a long time during the pandemic, because in Newfoundland and Labrador, it was mostly about imported cases. There was no community cases, so I didn't really have a lot to do in terms of modeling community spread, but I was kind of on the side interested in modeling importations. And I just did that statistically. And it was just on my computer, and it was just running, and it was actually pulling from this public data source, the Canadian Open Data Working Group. So this was just a script that I would just, it was pretty much at the top of all my other scripts to try and understand how many importations we were likely to have. And actually, this like data source ends in May 2021. But by that time, I had parameterized my statistical model, so I just kept doing it anyway. And so over here, this is like validated. It's like the parameters actually come from the gray region. And I was still running this on my computer, and it was super boring because it would just say every day, one travel-related case, one travel-related case, one travel-related case. And so I thought this was like a super boring script until like the Omicron variant. And then like they did this. And it was like a huge moment of panic, actually, when I like made that black line graph. But later, I actually got the data, which is the yellow, back. And then I thought it would be cool to do a validation of my statistical model. But I mean, I'm a mechanistic modeler, but this was some pretty good, well, the statistical model like did its job in that case. I think it was really awesome. So I want to follow up on this now because like I am a mechanistic modeler, so let's do some mechanistic modeling, but let's not throw out this whole thing. This statistical model was really like made its name for itself with that. Here's some mechanistic modeling, and we were getting this a lot through emails done by the Public Health Agency of Canada, and they would send emails all the time that were predictions from their mechanistic models about how many people were arriving in different airports and infected with COVID-19. So this is what they eventually published, the period from July 11th to November 27th. But this is a mechanistic model, and it's all entirely predictions. And I have to say, the entire time I was wondering, like, but what is actually the number of people that are arriving with COVID-19? Because I had this data all the time in Newfoundland and Labrador. It was getting reported very, very well. And I was like, I don't know, like it's a mechanistic model, it's making a prediction, but I don't know how accurate it is. So let's test out that idea. So I did a mechanistic model for the Newfoundland and Labrador situation, and I'm going to pretend I don't have any travel-related case data, and I'm just going to make the mechanistic model, and then I'm going to make the prediction of travel-related cases, and we're going to see, are these numbers actually close to what is the truth, or is it like super unreliable, which I definitely have seen some of this modeling in a super unreliable direction that there's no way that the statements in the papers could actually be true, because this is mechanistic predictions that are not validated at all. So this mechanistic modeling, there is no knowledge of the travel-related cases. This is going to be a pretty hard test of whether this model is reliable or not. So I guess, yeah, so there's quite a bit of detail that goes into that. Maybe I'll skip ahead a bit and just say that we considered all the mechanism. Like I didn't want to skimp on the mechanism. So there's different ways that you can be reported as a travel-related case in Newfoundland and Labrador. We parse those out. There are different regulations on who gets tested at different points in time in Newfoundland and Labrador. So we read that literature. People had to get tested if they were subject to an exposure notification. So we wrote that all down. Just like you do in mechanistic modeling, we considered all the parameter values, and we estimated all the parameter values from independent literature sources, as is common. Also in mechanistic importation modeling, you worry about how long was the person exposed ago, given that they arrived in Newfoundland and Labrador today? Like what are the days since exposure? And there's some mechanism that comes into this. So it affects the chance, if people are having pre-departure tests, then we had started with an assumption that you were, your date of being exposed was uniformly distributed between 14 days ago and today. But if you do pre-departure tests, it kind of eats into that uniform distribution in that way. If people are not going to travel because they develop symptoms, then that means that people that were exposed 14 days ago are extremely unlikely to travel because they're likely to have developed their symptoms before they leave. And it also affects the chance of getting a positive PCR test. If you're going to get tested because of symptoms, you're going to need to develop symptoms. So like all is to say that like every single thing that we could put mechanism into, we did. And I feel like all the mechanistic modelers in the audience are super nervous because obviously this could have gone hugely badly, but it actually didn't go so badly. So mechanistic model is at the bottom with 0 fitted parameters. And like we calculated the delta AIC and the log likelihood relative to statistical models. So the statistical models have a huge advantage. Those are actually fitted to the response variable, which is travel-related cases. And I mean, I guess this delta AIC value suggests that, you know, or the log likelihood suggests that the mechanistic model is way worse fit than the statistical models, but I don't know that I interpret it like that. I think the mechanistic model is really like, it's like a miracle that it came even close, I think. And this is for travel-related cases of Canadian origin. The international origin ones, the data is just a bit worse. Maybe I'd like to see a picture of the best statistical model. So again, maybe let's just do the top because that's Canadian cases and it's a bit better. The y-axis are like different scales. So it looks like different data, which are the black points, but it's actually the same data. And these are the fits of the mechanistic model and the best model. Mechanistic model has these spikes that are actually associated with exposure notifications on flights, which then people go in and get tested. I don't know. The best model has a good fit. I think the different scale on the mechanistic model is making it look like it's a bit worse. It doesn't look terrible to me, given that this could have been off by orders of magnitude. Agent-based models versus compartmental models. I don't really do agent-based models, but some people do, like Sayed Moghadis at York University. And I think this has been like some really nice work that people have done with agent-based models. I think both have their place, and I sort of highlighted why. Agent-based models have realistic assumptions, and that is very compelling. I think if you want to have public health take up your recommendations, they're going to ask you, like, did you consider the differences between the Moderna vaccine and the Pfizer vaccine? And a lot of different, did you consider all these details? The fact that you probably did for the agent-based model is going to help get a lot of assurance from the decision makers who maybe you want to follow your recommendations. That's definitely the strongest selling point for the agent-based models. But they also give up a few things that are important as well. So the compartmental models, the simple models also have their place, particularly because you can get results very quickly. And also because you can get insight into what's driving your results. And those are, I think, the two most compelling points. So basically, I don't really think you can, I think you need both because I think you need all those three strengths. And if you go with one approach, you're going to be missing a really important feature. Yeah, I mean, really, this is like sometimes the idea of agent-based models and compartment models gets conflated with issues of model complexity. Really, I feel like this is a picture of most of my models. Like, there's like something that is really important that I spend a lot of time on. Like, so for me, it's like often the importation modeling and then some other things. Like, I just have to have them, but like they're really there. They're not, I don't think they're driving my results. My model's not sensitive to it. So I just put them in because it has to be there. But I will spend a lot of time on the things that I think the outputs are sensitive to. So really, I guess this question, I think, boils down to if there are many processes that need individual level characteristics, then probably you need agent-based models. Otherwise, maybe you can do your realism through another formalization. Space stations or fire stations. This is about like regional modeling. So some regions for fire stations. So most of us experience COVID-19 in one place. And I think I definitely have had this experience that like you need to be consulting the local experts because you do, I just have observed some mistakes happen when people don't consult the local experts, and you really need to consult that. Regional characteristics determine the best public health responses, and small jurisdictions are under-resourced and their needs can be overlooked or falsely assumed in bigger conversations. So this is an update from the World Health Organization. When the pandemic first happened, it was recommended that there should be no travel restrictions that disrupt travel and trade, but All of the state parties of the World Health Organization then put travel measures in place. In July 2021, they updated their recommendations, and this is when we started to see regional factors come into what the World Health Organization was recommending. Local epidemiology matters in terms of whether travel measures are appropriate. Local public health performance and capacity matters. So these recommendations are saying that local factors matter. So these are some different words that get thrown around in public health about types of strategies: elimination, suppression, mitigation. One thing we've been working on is trying to have one model that will be able to accommodate all of these different strategies as a potentially optimal result under different regional conditions. So the elimination strategy, you try to take maximum action to reduce disease to zero. The suppression strategy, I'll skip over that in favor of mitigation, which comes up more. Or suppression, okay, so mitigation, you take action to flatten the peak. Suppression, you try to keep cases to a low number, but notably you're not trying to eliminate. And then also another version of mitigation would be circuit breaker, which is like intermittently having the measures. So these are all different public health strategies, but I think we need a general framework to say that given these regional characteristics, this region should be doing elimination and this region should be doing circuit breaker, etc. So we started discussing these ideas in this paper that Maria wrote, and like here's an example. This is sort of very qualitative, right? So we're just showing a gradient between elimination and mitigation. And there's three questions that you want to ask in terms of understanding whether you want to do elimination. One of them is elimination cost effective. And if you have a lot of GDP, like Ontario, then elimination maybe isn't that cost effective because you're putting a highly productive economy under restrictions. But if your economy is in this blow up segment, which is like a lot of the smaller jurisdictions, then maybe like elimination kind of is cost effective because the economy is not that large. Another consideration is the importation rate. So we kind of map different jurisdictions into this space. And then in other work, we took a framework. This is mostly based off this other paper by Hansen and Day, and that's an optical control paper. The optimal controls they get out of that paper can be recast in terms of these public health strategies: elimination, mitigation, or circuit breaker. And this is something that we did. And you get different things depending on whether you're a low importation region or a high importation region. That's a regional characteristic. So even that modeling that's done by Hansen and Day, they didn't frame it that way, but I think embedded in there is this idea that you can get different. You can reframe that in terms of the public health strategies, although that wasn't how they framed it. That's like something that we hope to write about soon. Okay. Small jurisdictions are under-resourced. The need for additional public health physicians is the most acute in rural areas, the Atlantic provinces, the territories and areas served by Health Canada's First Nations and Inuit Health Branch. That's a quote from a 2003 report. So we've been trying to draw attention to these issues. So we have this small jurisdictions modeling group. So these have all been reasons for fire stations, like to do with regional specificity needs. But I mean, there's also space stations. So it could be that the under-resourced jurisdictions like just work with the best experts, like we had SFU experts come in and help us with this paper. So you know, it's not to say that just because you live in Newfoundland, you're the only one who gets to do the modeling for Newfoundland. Like, I think there's also an argument for a space station lending help. So my conclusions about modeling philosophy: mechanistic modeling is undervalued. Both simple and compartmental models are needed. Region-specific modeling is needed, and this can be achieved by building modeling capacity in regional public health, which would be fire stations, regional experts in adjacent fields, such as epidemiologists, working with the support of modeling experts from the space station, or just having multi-jurisdictional representational modeling networks to draw attention to these issues. All right, this part is short. This is, so arguably the modeling is not the most important thing that we learned from the pandemic, I would say. I think probably the most important thing in terms of like whether you were able to do impactful modeling was probably more about the relationships than the actual modeling that you were doing. So there were, I worked in some groups that were groups of colleagues. So CanMod, Omni Reunus, MFPH, groups of colleagues. We also saw interdisciplinary groups emerge. So maybe I'll give the Ontario Science Table as an example of that, because that had some clinicians. The Modeling Consensus Table had modelers, interdisciplinary group, relationships with decision makers, relationships with the public. I think one of the main drivers of how successful you are in any of that is when colleagues say, you know what, Amy's doing some good work, like maybe like you would want to work with her. So I don't think this gets noted enough that it's what colleagues give you for referrals that maybe drives how much impact that you can have there. Pandemic preparedness means establishing the relationships and organizing your group of colleagues. And just in terms of like, I think we need to advocate for mathematical modeling as critical to the pandemic response. Like, I think if you're a math biologist, like, I think we need to keep like just arguing that this is important. I think this is maybe getting forgotten. It's good to build relationships, particularly with medical disciplines, participate in cross-disciplinary activities. Do training and knowledge translation on how to do good modeling. Like if you actually are a modeler, like it's good for you to do the knowledge translation as opposed to someone else. And I guess at the bottom I have be resilient, because sometimes it's hard to make any progress on some of these points. All right, so I do have my slides on my website if I've been going fast towards the end. So if you go to links on my website, you can get a slower delivery of these points. This has been my talk where I tried to argue that pandemic preparedness needs modeling preparedness and to think about some of the things that I learned from modeling during COVID-19. I would like to thank many people who helped me with even some of the graphs that are in this presentation, like they were actually the people that made them. So many different people here, ranging from a number of institutions. Like some of this help was like super critical and super important. So I really can't emphasize enough like how much some of these people helped us with our work and the trajectory of our work. Lastly, I would like to say my sincerest thanks to the Maud Menten Institute. I'm very happy to get invited to give this talk. It's been fantastic. And yeah, I will end it here because I'm over time. Sorry about that.
Maybe ask if I have any online.
Yeah, are there any questions online to start with, perhaps? Or yeah, or you can, if you have questions, you may ask them in put them in the chat.
Yeah.
Any questions here?
Can I ask
Yeah,
for
go for it. We
Okay.
haven't heard anybody online yet, so.
So when we're trying to model